V2G energy management system for electric logistic vehicle charging depots with battery energy storage systems. And my advisor is Professor Xuan Yishan. So the presentation is structured as follows. First, I will start with the abstract. Then I will move on to the introduction and our data tracking stage. After that is our V2G stage. Finally, I will show the simulation result and make a conclusion and usual work. So first is my abstract. Regarding the daytime charging, the SOC with TOU station avoid peak hour to reduce cost by 5% to 10%. However, compared to the pure SOC model, this cost saving comes at the expense of increasing waiting times. And the second is for our nighttime V2G stage. Our two-layer dispatch algorithm dynamic switch between game modes. Simulation converges with achieved cost saving of 21% in the low load condition and 27.3% in the high load condition. Finally, we have this study has integrated this finding into a Google Map-based UI to optimize route and minimize energy consumption for the vehicles. Moving to the introduction, this project aligns with the government's 2050 net zero pathway. So targeting electric vehicle to address the critical challenge of basic electricity cost and grid drain. Our projects are threefold. First is cost optimization. This study developing intelligent daytime charging stage gas balance SOC with the time of use precisely to reduce its distance. The second is the value creation. So we utilize the nighttime V2G technology to transform ideal vehicle into the stabilized energy asset. The third one is implementation. This study aims to build a practical real-time dispatch system verified by real-world data. The next one is our daytime charging station. So our goal is to minimize electricity expense without interrupt logistic tasks. To achieve this study established a real-time electricity price model based on Taiwan Power Company's high voltage two-stage TOU rates. As shown in the left figure, we divided the day into two parts, the mid-peak hour and the off-peak hour. So through the list, we can establish a price model for system to dynamically change our charging mode. The first one, the traditional parallel SOC model is strictly energy-oriented static. Its initial charge immediately whenever the battery drop below the threshold. And regard of the current electricity pricing, while this guarantees zero waiting cost, it carries a high risk of charging during expensive peak hour, which uniquely drives up operation expense. The next one is our time of use based charging static. So this is a cost-oriented static. When the battery drops below the threshold, the system compares the cost of immediate versus delay charging. As long as the delay is within the maximum asset waiting time, it selects the cheapest option to avoid peak hour without completion delivery schedule. So the next one, we compare the two different design of the charging station. The first one is distributed charging, and it functions as a charging anywhere model. It minimizes the deploy time by allowing vehicle to replacement energy at next one is our nighttime vehicle to grid V2G static. So the system architecture will as far as the feature shown in the feature. So we have 5 main components. The first one is our electric vehicle, and the second one is our battery energy storage system. So this is the DC system. In the next slide, we have AC system is our power grid and our home load demand. So in the center is our energy management system, our EMS system. So through the EMS system, we can control the power flow and control the system. So in the system, our main is to find the PD, the net load. So if the PD is positive, it means the system can need extra power to support. But if the PD is negative, it means the V2G static is to utilize excess energy. So in the layer 1 is our vehicle size decision. And each vehicle self-assists using its SOC and real-time prices against weekly rules. Rather than transmit raw data, the system will change the information into 2 key indicators. So the total charge demand and our total discharge potential. So in the layer 2 is the cloud side dispatch. Our EMS can through the PD to determine the system status. So if the PD is positive, it means the power defeat. The system needs extra power to support. And if the PD is negative, it means the power supply. We can sell the excess power to the grid. And take the MOSFET for example. In layer 1, we can know our EOVs with high discharging potential. So in layer 2, we can get a negative PD. So it means the power supply. And we find the battery status to the MOSFET. So MOSFET means the V2G. We can sell the extra power to sell back to the grid. And next one is our simulation result. So we compare the centralized and distributed charging stage under different maximum waiting time. The first one is the centralized charging. The cost decreased by 4.76% to 10.03% as waiting limit is increasing. But this is achieved directly at the expense of the increased bridge waiting time. Second one is distributed charging. A similar saving pattern occurs as the stage successfully shift charging situation to low price interval. So the next one is our pure SOC and our SOC with DOU static. Under the pure SOC, the distributed charging goes to be 16.9% more cost effective than centralized charging because it eliminates detour time caused by adding its eliminating detour time. By adding the SOC with DOU static, it study again additional 5%. In this section, we define the cost concurrence model to clarify our benefit. So the baseline is without V2G capability, where the total cost is simple the sum of EOV charging and the grid power purchase. But V2G has sold back to the grid, and it's a negative cost value, it means the profit. So in this section, we simulate a low load situation to demonstrate the financial supply of the V2G stage compared to the baseline. So the V2G stage reduced the total cost from NTD $3,714 to $2,931, is saving about 21%. And if by V2G, so the EOB's charging cost will increase, but the load cost will decrease. It means it don't need to rely on the grid power. In next situation, we simulate the high load situation. So the V2G stage reduce total cost from the baseline of 6,962 NTD to 4,767 NTD, and each saving about 27.3%. So in this session, we upgrade our research from a static simulation to a practical real-time dispatch system. So the system supports fast address, import, and restore fleet adjustment. Utilize real-time raw data to optimize flow based on distance, energy, and traffic conditions. Conclusion. This study summarizes three key contributions. Our SOC with COU stages reduce daytime cost by 5% to 10%, while the V2G operates achieve saving of 21% to 27.3%, depending on load condition. And we analyzed real vehicle data, and it's a nonlinear battery efficient. Established and optimal operation is 30% to 80%. And this study successfully built a particular real-time dispatch system that solves complex one-stop logistics challenge and bring the gap between simulation and application. So our future work we may add some new renewable power like the EV and use the DIO in our EMS system. This is my presentation.
Any question?
V2G involves different charging and discharging cycles, which can accelerate battery degradation. Did you account for battery depreciation cost in your total cost calculation?
So our battery operation mode is between 30% to 80%, and it is from the real vehicle data to analyze. So we use it to our circle. So our EOV's battery will not over the 30% or below the 30%.
Further question? Further question? Can you go back to the page 28? Okay. You have a real world experiment, but you do not show the total comparison or your performance improvement. 这个实际上的这个实验并没有说它的这个真实的这个数据。
对，因为我们后面是对，就是真的，因为我们后面是用那个真的物流车的数据来做我们实验的阐述，然后
you will combine your V5G algorithm into the real. Okay. Another issue is in the future work, you propose to design an ERL algorithm. Why will you choose such an algorithm?
Because
Yeah. Do you know why? Because it's not realized. 这是你想要做的，然后还没有被做。那你为什么会 propose？或者说你有什么样的这个想法？你这个意思的话，
因为像我们传统的 role base 来说，它是很多就是依靠专家经验来设计，
对，
不管是它的门槛值，或者是它的说什么它的限制。那我们就是现在的目标是让它自己去学习。那我们就是设一个硬体的最高限制给它，就让它不要真的把硬体烧坏。那我们是希望透过这样的方法去让它真的学出一个比较好的数据，因为像我们现在的门槛通常是30到80之间，那可能如果用 AI 的话，就是27、28这样子，它都就它会调一个比较好的操作曲线出来。不然像我们多倍的话，主要还是依靠自己设计专家经验。
Thank you very much. Okay, we welcome the next speaker.
Good morning, everyone. I'm Yu Zhang. Today, I will briefly introduce our work titled Web Optimization Algorithm Optimize Data Enable People Control with RSTM for Hybrid Electric Vehicle Energy Management. My presentation will follow these outlines. I will start with the introduction and system architecture. Moving to our proposed methodology covering RSTM, WOA, and VPC. And finally share the simulation results and conclusions. Let's dive straight into the current strategy in the pilot and try a new approach is necessary. Traditional energy management relies on physical models, which often fail when components stage in the planning version. To solve this, we propose a model-free data-driven framework. By integrating VPC RSTM and WOA, we eliminate complex modeling while ensuring robust adaptation to system nature. Now let's look at the overall system architecture of our proposed solution. Our firm will use an RSTM network as a predictive engine to forecast user argument from historical data. These insights allow the system to prepare for power spikes. Then DPC uses calculation parameters to manage the power flow between the battery and the supercapacitor efficiently. Specifically, DPC adaptively regulates energy flow without a physical model. This coordination ensures the supercapacitor handles high-frequency peaks, while the battery provides steady energy, which significantly extends the battery lifespan. Next, I will detail the first part of our methodology, RSTM-based definition. Traditional reactive controllers suffer from response lags because they only respond after a load change has occurred. Our RSTM network solves this by analyzing historical data to forecast future power generation patterns. This allows us to selectively recharge the supercapacitor to buffer power peaks. Here is the internal structure. The input layer captures the recipe sequences, and the LSTM layer identifies the temporal dependencies like tracking or acceleration. The fork connect layer maps these features into a recipe variable. And finally, the output layer generates a trajectory, which is converted into power domain for control. Now let's look at how we optimize the control parameter using the flow optimization algorithm. WRA means the function behavior of convex flows, and shown in the flow chart, it uses three modes: search, encircling, and the bubble net attacking to prevent local optima and ensure precise conversions. Through this process, WRA identifies the ideal weighting metric, Q and R, for maximum efficiency. We apply WRA for offline parameter tuning. We target for keywords, current penalty, and the state of charge shifting penalties for both the battery and the supercapacitor. By minimizing total energy use, WRA ensures the real-time controller balances energy saving and conformance protection effectively. Now let's discuss how the high-level predictive control or DPC brings everything together. DPC treats the system as a black box. We collect control inputs and the state output directly and step them into a Hankel metric. This metric creates a data library that implicitly describes the full dynamic behavior of the system without needing physical equations. Since the system is underdetermined, the Hankel library supports countless potential trajectories. To select the single optimal one, we rely on the cost function. The solver picks the specific factor G that results in the lowest energy cost. In this formulation, metric Q reduces energy loss by suppressing high currents, while R ensures that SOC levels track their preference. Crucially, we enforce a power balance constraint to ensure the physical output strictly meets the driver demand at every moment. To complete the loop, we use WRA for offline tuning and a continuous feedback loop for real-time operation. As every time step, real-time measurements update the buffer, allowing the controller to instantly adapt to changing load conditions. Let's look at how this performs in simulation. We compare our method against the rule-based control logic. This benchmark relies on static threshold and switches between discrete modes. Its main limitation is the lack of loop effect capability, making it unable to achieve the global optimality that DPC offers. First, for LSTM validation, the model tracks the speed profile with exceptional precision, achieving an R-square of 0.97. This accuracy is vital for providing reliable power demand inputs to our controller. Looking at the quantitative results, our LSTM DPC strategy significantly outperformed the benchmark. We reduced total energy loss to 0.5 kWh, a 20% improvement. Furthermore, battery stress are mitigated with an 80% reduction in current cooling speed, effectively extending the system lifespan. The battery health analysis shows this video. The rule-based logic shows directive oscillations, while our WRA-DPC strategy ensures a much smoother and a stable battery profile by loading peaks to the supercapacitor. A unique feature of power control is reactive recharging mechanism. By leveraging LSTM forecast, the controller identifies the incoming high demand and proactively uses the battery to recharge the supercapacitor during low load interval. This ensures sufficient capacity to absorb surge and reduces the voltage rates. This brings us to the final part of my presentation. To summarize, our research successfully integrates LSTM and DPC, while the Model 3 baseline already showed a 40% improvement. ABWA optimization reached the peak performance, a 20% reduction in energy use, and 80% reduction in battery use recurrence. This complements our strategy to provide a robust, high-precision solution for achieving energy management. This brings to the end of my presentation.
Any questions?
Introduction states that traditional physical models will be accountable for optimization. How exactly is DEPC's continued updating of the past trajectory that solve this creating problem in real life?
Fixed system mathematical equation cannot automatically change itself when the battery loses capacity over years of use. Because DPC continuously is the most recent real-time input and output, measurement back into the metric battery. The controller understanding that the system is always based on the battery currents, regulated physical state rather than an outdated battery assumption.
Further question? Okay, here.
The WOA is used successfully for offline parameter tuning before the system upgrade. Why is this optimization calculated before the car is driven rather than in real time field?
More intelligent algorithm requires simulating thousands of interactions to find the absolutely best parameter combination. Performing this heavy computational routine performs against the vehicle onboard processor from being overloaded and ensure there is zero population rate. The controller needs to make frequent power adjustment during actual value.
Okay. Please go back to the comparison page.
The first one is the rule fence and next SDN dip control, and next one is plus the wheel optimization algorithm. In such a comparison, you can see that SDN plus dip control has a significant improvement, and are you plus wheel optimization? It seems like minor improvement, about 6%. So maybe the second one can do improvement. It shows very powerful. How will you use WOA? It seems minor.
我觉得那个 WA 好像